In the second lecture, we concluded that the Einsteinian equivalence principle is satisfied if the gravitational field is represented by the metric, and then the connection represents a sort of field strength. It's certainly related to the Newtonian field strength when we take the non-relativistic limit. But so far in what we have studied, the way we have introduced the connection through parallel transport, the connection is something which is completely arbitrary. And it could be good to know which possibilities there are for the connection. In order to relate this connection, this general connection, that we can choose almost arbitrarily with the connection that is associated to the Einsteinian equivalence principle and that we can use to do physics and to represent the gravitational field. Well, it can be proven that the most general connection that you can write can be decomposed in three pieces. The first piece is a function, if you want, is a tensor, but okay, that depends on something that I'm going to define just in a second, and I call Q. Another piece that I'm going to represent by this K mu nu rho, which depends only on the torsion. And maybe on the metric. I mean, these two terms may depend also indirectly of the metric to raise or lower indices, but nothing beyond that. Plus a third piece that I will write like this, which only depends on G and derivatives of G. Okay. But the main property of these two pieces is that if the torsion vanishes, this piece vanishes. If this Q vanishes, this piece vanishes. So what is Q? Q is the non-metricity tensor, and it is defined as the covariant derivative of the metric. Okay, and this F mu nu rho is some construction in which you have to raise indices and permutate indices, but it is built out of Q. Okay, this piece F has no specific name. This piece K mu nu rho is called the contortion tensor. And vanishes when the torsion vanishes. Again, it's a combination of T with some indices raised and some indices lowered. Okay, so this is probably the only piece that we want to keep, the one that could represent the gravitational field and nothing else. So what we are going to do is to demand from our connection that it has these two properties. Okay, so first of all, mu nu rho should be 0, or equivalently, okay, the covariant derivative of the metric is 0. A connection that satisfies this property is called a metric compatible connection. Or a metric connection sometimes. And the other condition that we are going to demand is that the torsion is 0. Okay, then the contortion will be 0. And this is a torsionless connection, obviously. Now, if you wonder if this gamma mu nu rho, which is only a function of G, and delta G is unique, or it can be modified in some way with some parameters, the answer is no. There is a unique connection which is determined by these two conditions that we have imposed right now: metric compatibility and absence of torsion. The resulting connection, which has this satisfies these two conditions, is the Levi-Civita connection. And since it depends only on the metric, it fits perfectly within the Riemannian geometry or pseudo-Riemannian geometry. So this is the connection that appears in general pseudo Riemannian geometry. So now what we are going to do is to prove that under these two requirements there is only one connection, and we are going to find the components of this connection for a given metric in some coordinate patch. Okay, so how do we do this? We are going to use this property that the connection is metric compatible, so this is 0. And I remind you what this covariant derivative is. It has this piece, and then mu sigma g sigma rho minus g mu rho sigma g mu sigma. Okay, the goal of this exercise is to find the expression of this g, this gamma, sorry, in terms of partial g and g's. So how do I do that? Well, I am going to write the same equation, but now with the indices shuffled. So I permute them cyclically. Okay, so now I am going to write this. And I get this. So rho goes to mu sigma g rho sigma. And again, I write another permutation of the indices. Again, this is 0, but the expression for this is g mu nu minus rho mu sigma g sigma nu minus mu goes to rho, mu goes to nu, and sigma g mu sigma. Okay, and what I am going to do now is to combine these three equations with this sign. So I sum this one and I subtract this one. So okay, this gives me 0 in all cases. So I get partial mu g nu rho plus partial nu g rho mu minus partial rho g mu nu. Now, how about the terms that involve gammas? First, you have to take into account that we are imposing absence of torsion. Okay, remember that this is the same as imposing that the connection is symmetric in these two indices. Okay, if it is symmetric, then you compare this term and this term, okay, and they are the same, okay, with the same sign, because gamma nu mu will be the same as gamma mu nu, and what the metric is symmetric, so g sigma rho is the same as g rho sigma. So I get minus 2 gamma mu nu sigma g sigma rho. Now I compare this term and this term, again using symmetry. So these two terms have the same indices, okay, once I take into account the symmetry of the metric and the symmetry of the connection, but because of this overall minus sign here, this one has opposite sign to this, so they cancel. As for the two remaining terms, this one and this one, you see that the same happens here. They are identical up to the overall sign because of this overall sign that we have chosen here, so they also cancel, and this is the result. Well, now I can multiply this by g rho alpha, for instance, and then I get g alpha rho partial mu g mu rho plus partial nu g rho mu minus partial rho g mu nu, and minus 2 gamma mu nu alpha. Okay, so this is equal to this, then I divide by 1/2. And you see that the answer is unique, so there is a unique connection that satisfies these properties. And the answer is, and the form of this connection, the components of this connection are given by these partial derivatives of the metric computed in this way. This combination of partial derivatives and so on are usually called, well, they are denoted by this. These are called the Christoffel symbols. Okay, so the Levi-Civita, the components of the Levi-Civita connection are given by the Christoffel symbols in some coordinate paths. Okay, so a lot of the calculations that you will do in this course will have to do with computing these the components of this connection using this formula, as you may expect, because you want to compute connections because they represent they give you important information about the gravitational field. So first of all, let me just explain you how you will never forget what these components are. So the idea is that, okay, I know that I have to multiply everything by I have derivatives of g, 3 derivatives. Okay, one of them comes with a minus sign. Since all these 3 objects have lower indices, you have to multiply by the inverse metric to raise it. Okay, and this index has to be here. Then there must be another index that is contracted with indices of these partial derivatives. Exactly how? Well, so one of them is here, the other one is also here in G, and the last one with the minus is here. And this thing is symmetric, so okay, these 2 terms must be like this, because otherwise you wouldn't have symmetry. And the last term is symmetric automatically in mu and nu. So this is just to help you to remember what is the structure of these Christoffel symbols, because as I said, you will have to compute them many times. And what could have happened if we didn't set to 0 the torsion and this metricity tensor Q? Well, they are tensors, so clearly I can set to 0 this connection at a given point, which is one way of satisfying, or the way to satisfy the equivalence principle. You can check, if you have the patience, that these Christoffel symbols transform exactly the way we said a connection had to transform. Then to this Levi-Civita connection you can add other tensors and it still transforms in the same way. Okay. It will transform as a connection because you just need something that transforms as a tensor plus this inhomogeneous term. The Levi-Civita connection provides this inhomogeneous term, so the rest can be any tensor. Doesn't really matter. But then, okay, again we were trying to set to 0 a gamma at a given point, and if these terms are different from 0, okay, since they are tensors, you cannot set them to 0. You can set to 0 this part. And it is very difficult to set the combination, all the combination to 0, because you see this is symmetric, but all these pieces contain, at least this one, certainly contains pieces which are antisymmetric. It is very difficult to make a coordinate change, okay, which contributes with this inhomogeneous term, but it's inhomogeneous but symmetric, because it will preserve the symmetry of gamma in such a way that it cancels the antisymmetric terms in K. So probably you conclude that by including this torsion and metricity tensor, the equivalence principle could be violated. Well, if again, the equivalence principle is a principle, but it has to be checked experimentally. But really, the experiment set a very strong limits on any possible violation. So if there are terms like this f of q and this contortion tensor, in nature they are very, very small. Another problem that you have is that q and t are tensors different from the metric. They are not determined by it. Okay, this looks a bit confusing because it looks like it is the metric that determines q, but if you look inside of this expression, there is the connection, and this really tells you that there is a piece of the connection which is q. It is not, but q is not completely determined by g. Then, well, you cannot have just some fields in your theory with some values, because that could probably violate all kinds of symmetry principles. The only way to make to include them in your theory would be to make them dynamical fields. This is not easy for a generic metricity tensor, but it can be done for certain simple metricity tensors. And for the torsion, well, the truth is that there are many theories that give you torsion in a very natural way, in particular when there are fermions. So theories with fermions in Corte space, it is very natural to have torsion. And okay, we cannot discuss this much more, but there are ways in which one can make the presence of torsion, at least, compatible with experiments with the principle of equivalence, and then not introduce too many problems in your theory. Okay, from now on we will just work with the Levi-Civita connection and with no other connection whatsoever, unless we mention it explicitly, and I think we will only do it once when we describe what an autoparallel curve is in general. For the rest of the course, we will only consider the Levi-Civita connection. We will do pseudo-Riemannian geometry. The metric field will be the only independent field, and we will be computing Christoffel symbols quite a lot. So the rest of this video, we want to study the main properties of the Levi-Civita connection and of the curvature that depends, which appears when you have this connection. Okay, so these properties. The first of them is that is obvious. We just said it, that it depends only on the metric through the metric itself and its derivatives. Okay, the second property is that it is symmetric. Okay, it's part of the definition. Oops, this is not symmetric, this is just wrong. And the third property also comes from the very definition, but it has many operational consequences, is that the covariant derivative with this connection, but I don't need to say this anymore because this is the only connection we are going to consider, that applied to the metric gives you 0. This fact is sometimes expressed as saying that the metric is covariantly constant. You see that in this general context of differentiable manifolds, it does not make sense to say that a tensor is just constant. Okay, because if I write this quantity and say, okay, this is 0, well, this is not a tensor, which means that when I transform it, I will get some inhomogeneous terms, and maybe in a different coordinate system it will be different from 0, at least some of the components. What really makes sense and is a statement which is independent of the coordinate system is to say that something is covariantly constant. So the covariant derivative applied to it gives you 0, because this statement is true in any coordinate system, because transforms is a tensor and transforms homogeneously under coordinate transformations. Okay, so the question is, what happens with the inverse metric? Is it also covariantly constant? Okay, in order to answer this question, we are going to do as follows. So first, let's consider the covariant derivative of the Kronecker delta symbol. Okay, it's a tensor. And okay, it is a tensor that you can check that it always is a delta in any coordinate system, because you multiply with a Jacobian from one side, an inverse Jacobian, and they always give you another delta. So this tensor is actually constant, literally constant in any coordinate system. Let's see what the covariant derivative is. So by definition, okay, then it has a term with a plus, rho, mu, and something to sum over, and a term with a minus, mu, sigma, delta, sigma, rho. Okay, this is 0 because it is, the delta is constant, and this term is mu, rho, and the second term is mu, and rho. So it is 0. So the Kronecker delta is covariant, it's constant and also covariantly constant. But this we can write as G nu alpha G alpha rho. And because the covariant derivative satisfies this Leibniz rule, okay, this is the derivative of the first times the second plus the first times the derivative of the second. The derivative of the first is 0 by definition, this property here. So this is just mu G alpha rho. Now this is 0, we just calculated it, okay. This is this 0 here, and the conclusion is that the derivative, the covariant derivative of the inverse metric is also 0. You can multiply the inverse metric by the inverse metric, this expression, if you want, but you can also just think that for a generic metric which is not singular, the coefficient, and if this is 0, then these coefficients must be 0. So the conclusion is that this is also 0. And so these three properties are something to remember. Because you are going to apply this many times. In particular, you will use it in this way. So suppose that I have covariant derivative of a contravariant tensor, and I want to lower, this is a 1, 1 tensor, and I want to lower this index. I would do it multiplying this by G alpha nu. But for a generic connection, well, I need to put this metric inside of the covariant derivative, and it is not clear what the result would be. However, here, this is just nabla mu of G alpha nu psi nu minus alpha nu psi nu. This is just, we have lowered the index, and this is 0 because the metric is covariantly constant. And of course you can do the same with, now you can raise a lower index by multiplying with the inverse metric, because it is also covariantly constant. So you can introduce the metric at will inside of the covariant derivative. That's the main consequence. Okay, Another property which is very useful is that if you contract one of the upper and one of the lower indices, okay, and because this is symmetric, this is the same as this, then what you get is the partial derivative of the log of the square root of the determinant of the metric. Okay, I remember I used these bars to say that I take the absolute value. So in my conventions, this determinant will be negative, and this is equivalent just to take to write minus g. But for some reason I don't like it. I prefer this absolute value. Okay. So here this g is the determinant of g mu nu. Maybe I didn't define it before. Okay. So let's prove this property. Okay. So we can compute this, and this by definition is this contraction of the Christoffel symbols. Now, in the inverse metric, this index comes here. Okay, remember that these two have sigma there, and then this, and then the lower indices come here, symmetric form. Okay, so this is what you want. And now the expression inside of the brackets is contracted with mu and sigma, which is symmetric. This term has mu and sigma, and this term has sigma and mu. Okay, let me write it if you want in a more explicit way. This is symmetric, so you have only the symmetric part here. But okay, this is the same as partial mu g sigma mu, because the metric is symmetric, so we can do that. And because of the symmetry of this expression, which is symmetrizing mu and sigma, this is partial sigma g mu and nu. So the conclusion is that this term and this term cancel, and okay, only one term survives. And it is this one. Okay, so now we need to use this property of the derivative of the determinant. Okay, this property could be equal for any the determinant of any square matrix, and this property tells you that this is new row times the determinant itself. So using this here, you conclude that this is 1 over 2g partial nu of g. Well, you could take absolute values here, which would be multiplying by minus up and down, and you see that this is the partial of the log of g with 1/2, but then I can put the 1/2 inside, and this is just the square root, which proves what we wanted to prove. This has several consequences that simplify our life. For instance, if you want to compute a covariant divergence, remember that we called divergence this in the Minkowskian case. So when we do it, we take the divergence with the covariant derivative. This is the covariant divergence, and the consequence is that this can be written in this way. Okay, so instead of writing the whole thing with the connection, we just need to know the determinant of the metric, and we just have to compute this. Of course, we have to prove it. So there is a plus, remember, Now this gamma has the upper index mu because it is a contravariant tensor. It also has this lower index mu because it is here, and then the index over which we are going to sum. And now we use the property we just proved about gamma, well, this property 4, and this is 1 over square root of g partial sigma square root of g psi sigma, and you can immediately see that this is the same as this. Okay, because if you take the derivative with respect to the square root, you get this times psi mu plus a term with divergence and the square root up and down, they cancel, so they are the same thing, which proves this property. Okay, then another consequence which is derived from this, if I compute box phi, and box phi now in general will be nabla mu phi. Okay, sometimes we express this as nabla square phi as well. Okay, just applying this property, you see that this is 1 over the square root of g, and the partial derivative of phi. Well, why? Because the first covariant derivative is just a partial derivative, it's identical to this, so you apply this formula here to this contravariant tensor and you get exactly this. This is another formula to remember, and really this simplifies many calculations, because always computing components of the connection is much more difficult than computing the determinant of the metric. Now a final property of the same kind, which also follows from the above property, if you have an antisymmetric tensor, such as the one of the field strength of the electromagnetic field, then okay, this is the covariant version of the Maxwell, what appears in the left hand side of the Maxwell law, or the Maxwell equations, then this is equal to this. Again, we don't need to compute all the components of the connection. We prove this immediately, so there are only plus signs, and this first term is just like this. Oops, this should be sigma, sorry, sigma nu, and then there is another term when I take the derivative, they consider the second index, okay, which is f mu and sigma. Now this second term with the Levi-Civita connection, this is symmetric and this is antisymmetric. These two indices are contracted, so this second term vanishes. This one is 1 over the square root of g partial sigma square root of g, and just like we did before, this is equal to this. Okay, so this is the proof and the final property. And then a warning, or something to observe: if you have a tensor such as the energy momentum tensor, which is symmetric, then if you want to compute the divergence, then this is not proportional to the standard divergence. Okay, so in particular, because there is a term like this that doesn't vanish, we cannot argue that the connection is symmetric and the tensor is antisymmetric. Here both things are symmetric. So in this case, there is an extra term. This should be, sorry, gamma mu sigma nu and t mu sigma, which doesn't vanish. Why is this important? Well, it is important because conservation laws are related, or are expressed, local conservation laws are expressed through the continuity equation in this form. Okay, if we have a current okay, now this statement is clearly not covariant because the partial derivative is not a covariant derivative, but we can really generalize it to something like this. So conservation laws will be expressed by something like this in curved space-time. And the fact is that there is a relation between these two things, because up to this factor of square root of g, okay, now you could say that well, it is the same equation, but instead of an equation involving just the current, it's involving the current times a square root of g, and it is still the same. However, when you go to this expression here, at some point we will get an equation of this form, and you want to ask if this can be understood as a generalization of this to curve the space-time, and then it can be interpreted as a conservation law. But then if you look here at the right hand side, you see that okay, this first term corresponds to a divergence more or less like this, but there is another term, so this is not a conservation law. Okay, although it is the obvious covariant generalization of this law, the moment you write it like this with a covariant derivative, it doesn't work like a conservation law anymore. Is this a disaster? We'll see, but it is a very important thing to remember. Okay, next property, which is not longer related to this particular property of the connection that can be expressed through the square root of the determinant of the metric, is what are the Bianchi identities when we work with this Levi-Civita connection. Okay, well, all the Ricci identities that we found before will be satisfied with t equals 0 in particular. Let me remind you how it works. Well, first the Ricci identities. So if you compute this on a function, now it is 0. So let's say Ricci and Bianchi identities. Okay, this is the Ricci identity now because there is no torsion. This means that the covariant derivatives acting on scalars commute. So this is the same as this, only on scalars. Now you go for the next Ricci identity, and this is just r mu nu alpha sigma psi sigma and nothing else. So now the covariant derivatives acting on vector fields do not commute. The tensor that appears here and which is only a function of the Levi-Civita connection is the Riemann tensor. So it is the curvature tensor of the Levi-Civita connection. The last Ricci identity, just for completeness, is minus r mu nu alpha sigma omega sigma, and for higher order tensors, you know, Okay, and for the Bianchi identities, you just take those that we computed before and specialize for the case t equals 0. So one of them was trivial, or quite trivial. The curvature tensor, the Riemann tensor, is antisymmetric in the first two indices. The second identity is that the fully antisymmetric part of the first three indices is 0, and because it is antisymmetric in the first two indices, this is the same as R alpha beta gamma delta plus R beta gamma alpha delta plus R gamma alpha beta delta equal to 0. Okay, with a factor of 3. If I multiply this by 3, this is what I get, and it is equivalent to this. And the last identity, the one I told you that could be transcendent in our study of gravity, is this one. Delta, say epsilon, equal to 0. And okay, again I can express this as 3 terms, R beta gamma delta epsilon, and it's only these 3 terms that I have to interchange cyclically. Gamma alpha delta epsilon plus nabla gamma R alpha beta delta epsilon equal to 0. It is the same thing. Okay, and these are the ones you want to remember. But we can do a bit more here, because we can apply this very easily to the metric tensor. And what is this? This is 0 because the covariant derivative on the metric tensor is 0. But according to the general Ricci identities, this is minus R mu nu alpha sigma G sigma beta minus R mu nu beta sigma G alpha sigma. So this is equal to 0. And you see that this is minus R mu nu, and now I use the metric to lower this index, nu beta alpha, and this is minus 2 R mu nu alpha beta, and this is 0. So we get an extra Ricci identity. The Riemann tensor is not just antisymmetric in the first two indices, but it's also antisymmetric in the last two indices when you lower them. So this is a further Bianchi identity. And now you can use a combination of this one and this one to prove is a derived identity. Okay, this is clearly not independent of them, but that we will use very often. I think it is called sometimes interchange property, but don't trust me too much on this because I'm very bad for names. So let me compute alpha beta mu nu, and because of this property here, this is minus R beta mu alpha nu. I only permute cyclically the first three indices, minus R mu alpha beta nu. Okay, now I apply this property here, the last one we have derived, and well, I have R beta mu, but then I interchange alpha and nu, so I get a plus. And I do the same with the last two indices here, beta and nu. It's plus R mu alpha nu beta. Okay, now I use this property again. Okay, with the first and the second Riemann tensor. So this will be equal to minus mu nu beta nu, sorry, alpha minus R nu beta mu alpha. The last index is untouched, and the other two are permutated cyclically, and here is minus r alpha mu beta minus r mu alpha beta. Okay, I get two terms which are identical, okay, this one and this one, because now this is antisymmetric, this is also antisymmetric. So I get 2 times r mu alpha beta. I interchange this and I put it in this order, alpha beta. Okay, the next term I just interchange these two and I get plus r nu beta alpha mu, and the other one I also interchange the last two indices. I get r alpha nu beta mu, and you see that this term and this term, okay, they have the form of well, in this you can obtain the second by a cyclic permutation of the indices of the first, or vice versa. So they give me, again using this Bianchi identity, only one term, so it's r mu nu alpha beta, and then minus the only one that remains is r beta alpha nu mu. Okay, now I interchange these two to put them in the standard order, and these two. So this is 2 r mu nu alpha beta minus, because I have two minus signs, r alpha beta mu nu. I take this term to the left hand side and I get 2 times r alpha beta mu nu equal to 2 times r mu nu alpha beta. The factors of 2 go away, and what I get is an identity in which I have simultaneously interchanged the first pair of indices and the second pair of indices. Okay. Well, now we have determined many symmetries of the Riemann tensor. We can one of the consequences of having all these symmetries is that only a few components will be really independent. Okay, there is a great redundancy in the description of the independent components of the Riemann tensor. So how many components are there independent? Well, let's compute this in d dimensions. You can look at it from this point of view. You have this pair of indices which is antisymmetric, and this pair of indices which is also antisymmetric. Look at this as a matrix whose index with two indices, one is this and one is this. It is not simple index, but okay, it goes from 1 to d times d minus 1 divided by 2 in both cases. This is what happens when you have indices which are antisymmetric and in d dimensions. The first can take d values, but the other one cannot be repeated, so you have to multiply the d values of alpha times the d minus 1 values of beta, and then divide by 2. Okay, so this is the whole range that this pair of indices can take. So in total, since this is symmetric in this interchange of indices, okay, you can look at this as a matrix. Well, let's not use that property, the symmetry, because we can use either that one, this property, or we can use this one. We cannot use all these properties at the same time because it would be redundant. So instead of using this property here, okay, and saying that this is a square matrix with indices which are represented by an antisymmetric pair of the other indices, we would use this constraint, okay, this Bianchi identity, to subtract the number of constraints, that is conditions, that is relations between the components of the Riemann tensor. So how many are there? Okay, when you have three antisymmetrized indices like this, you have the first can take d values, the second can take only d minus 1, and the third d minus 2, and you can permute them, so you have to divide by 3 factorial. Delta is independent, so you have all this. And the total of independent indices is this quantity minus this quantity. Okay, it's a not so difficult calculation, and believe me that the result is 1 over 12 d squared minus 1. Okay, so in 4 dimensions you have 10 independent components, sorry, 20 independent components. In principle, they might have been, if this the Riemann tensor was didn't have any symmetries, it could be 4 to the 4th, so 16 squared, which is quite a lot of independent components. Well, this is algebraically independent, but we must remember that we can make changes of coordinates that can eliminate certain components. Not all of them, because if the Riemann tensor is different from 0 at the point, it will be different from, in some coordinate system, it will be different from 0 in any coordinate system, but you can find combinations of them. And this is a much more complicated calculation. Since coordinate transformations also reshuffle the components, they combine them, and so on, another way of characterizing, a better way of characterizing the components of the Riemann tensor is through curvature invariants. These curvature invariants are scalars constructed from the curvature tensor. The simplest one would be r mu nu rho sigma, r mu nu rho sigma, and okay, it depends on the metric and on the curvature tensor, but the advantage of this is that it is some scalar, so it always has the same value in any coordinate system, and clearly it represents some of the information which is contained within the Riemann tensor, but in an invariant way, just as we studied the invariants of the Maxwell field, and we found that there will be this one that we called f squared. There was another one that we wrote in this way, and they give you information, invariant information about the electromagnetic field. Well, there is a number. There are more that we will describe, but this is something that has to be taken into account. And when we discuss the characteristics of the gravitational field, which are independent of the coordinate system, we will have to resort to these curvature invariants. Finally, another thing that has to be taken into account are the Bianchi identities, the differential Bianchi identities, which is this one, which relates in a more complicated way the components of the Riemann tensor. Okay. So this can look very complicated, how to characterize gravitational fields through the Riemann tensor, even if there are only 20 independent components. There is a theorem which it is a very important theorem, and well, you have to learn it, and it establishes a very important relation between the curvature tensor and a given metric. So this is the theorem. A Lorentzian, so it's a plus minus 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 metric is flat, and flat means here a piece of the Minkowski spacetime. Okay, expressed in some coordinate system. And here the word metric is missing. If and only if its Riemann tensor vanishes. Identically. Okay. This means that, well, I am given a metric, a very complicated metric, in some coordinates. I start computing the curvature tensor and I get that all the components are 0. Okay. This must be in that region, not at a point. Then what I know is that this metric, which can be very complicated, is just the Minkowski metric in some part of the Minkowski spacetime, maybe not all of it, but it's just the Minkowski spacetime, a part of the Minkowski spacetime, which is the points, okay, and the Minkowski metric put on it, and vice versa. Okay, if I have the Minkowski metric, I take a piece of it, I change coordinates no matter how, I know that the Riemann tensor will be identically 0 when I compute it. This is a very powerful theorem and something worth remembering.